In R.4, we're going to look at rational expression. So something to remember is when we say rational expression, remember this is a ratio. Ratio is a fraction. We're looking at expressions of fractions. They're ugly because they're going to have polynomials in the numerator and denominator, which means there's going to be variables. So the first thing we're going to do with our rational expressions is we're going to find the domain. So remember, the domain is our universal set. It's all the things that we can choose from, or all the things that we can put into our rational expression. With rational expressions, since they are fractions, the only time we're going to have a problem is when the denominator is 0. So it's real simple to find the domain for a rational expression. You just have to figure out when the denominator is 0 and then take those out of the domain. In example 1, we need to find the domain of the expression, and then we need to write it in set builder notation. So set builder notation may be new to you. So I will introduce it in R4, and then we'll explore it further in chapter 1. Part A, we have the expression 1 over x plus 7. It's a fraction. I'm going to have a problem when the denominator is 0. So that happens when x is equal to -7. So if x is equal to -7, I get 1 over 0, and this fraction or rational expression is undefined. So I can't use -7. To write this in set builder notation, you would first use your set braces because it is a set. And then you have to state what variable you're talking about. Oftentimes we'll have more than one variable, so we have to be specific. We're talking about our x's. And then we're going to put this bar. This literally translates to such that. So far this reads the set of all x such that, and all I have to do is put my condition that x cannot be equal to -7. And that is the domain. I can use any x except -7. Okay, let's try this again in part B. Notice that in part B, there is a variable x in the numerator, but that doesn't matter with a fraction. The numerator can be any value, even 0. It's the denominator that we have a problem with. Now, if you can't see what x value will make the denominator 0, simply set the denominator equal to 0. So we have 3x minus 10 equal to 0, and solve to get x equal to 10 over 3. So remember, x cannot be equal to 10 over 3. That's our problem, which means our domain would be all elements x such that x cannot be equal to 10 over 3. In other words, I can use any x except 10 over 3. Again, we'll explore set builder notation further in chapter 1. Let's look at another example. In example 2, we want to find the domain and then simplify the expression. And this is really important when you're dealing with rational expressions. If you have to find the domain, you want to find the domain before you simplify. Remember, this is a fraction. Maybe it can be reduced. Maybe I can cancel some stuff. In order to determine the domain, I need to factor the denominator to see where it's going to be equal to 0. And in fact, I'm going to factor the whole thing because the second part of this is to simplify. The only way you could simplify a fraction is if you can cancel factors from the top and bottom. To be able to cancel factors from the top and bottom, it has to be factored. So in the numerator, I can factor out as 3 to get m squared minus 9 in parentheses. Now remember, whenever you factor something out, what remains is in parentheses. In the denominator, I can factor out a 9, and then I'll have m squared plus 2m minus 3. So already I can see that I could probably factor further. In the numerator, and I could see that I can reduce the 3 and the 9, but I'm not going to do that yet. In the numerator, I have a difference of squares. This would be m plus 3, m minus 3. in the denominator, the trinomial will factor as m plus 3, m minus 1. So it's completely factored, and I could see that I could reduce the 3 over 9, and I can also cancel the m plus 3 top and bottom, but I don't want to do that yet. I want to state the domain first. So if we look at the denominator, I can see that if m is equal to negative 3 or m is equal to 1, I'm going to have a problem. So m cannot be equal to negative 3. M cannot be equal to 1. Otherwise, the denominator will be 0. And this would be my domain. Sorry about the major rooster issues. The set of all m, because my variable is m, such that m cannot be equal to negative 3, m cannot be equal to negative 1. Now remember, in sets, we're allowed to, list elements by separating them with commas. There's a more efficient way to write this domain, and this would probably be what you would see in your textbook or in my lab. Instead of writing m not equal to negative 3, m not equal to 1, they will write m cannot be equal to negative 3, comma 1. Both of these are correct. So this would be the domain. It's the domain of our original expression. Again, we want to find the domain before we reduce. So let's go back to the simplification. Notice that in this expression, I can cancel the m plus 3 top and bottom, and I can reduce the 3 over 9. What will happen is I'll end up with m minus 3 over 3 times m minus 1. Notice in this simplified expression, the m plus 3 is gone. So if I were to find the domain after simplifying, I lose the m not equal to negative 3, which again makes the original expression undefined. So that's my caution. If you're finding the domain for a rational expression, find the domain before you start reducing and canceling. When we're looking at rational expressions, they can get pretty ugly. So oftentimes we just leave the answer in factored form. Notice I didn't distribute this 3 in the denominator and write 3m minus 3. It's not necessary. In fact, it's preferred to just leave it in factored form. Let's move on to some other properties with rational expressions. The first thing we're going to do is we're going to review multiplying and dividing rational expressions. So remember, these are just fractions. When you multiply fractions, you just multiply numerator, multiply denominator. However, since they are fractions, we always have to make sure that they're reduced. So we have to factor and cancel. So it's easiest when you're dealing with rational expressions to do the canceling first. Remember, we're allowed to reduce first with fractions and then do the multiplication. And that's always preferred. It'll simplify your computations. So example 3 part A, I could see that the numerator factors into 5 times n plus 5. Denominator factor out in n, and we have n minus 1. So remember, every time you factor out, what's left over is going in parentheses. Times the 10n stays. Denominator will factor as n plus 5, n plus 1. So I can see that I can cancel the n plus 5, top and bottom, and also an n. So now that it's reduced, I'm going to do the multiplication. The numerator is 5 times 10, so I have 50. I don't know why this is having problems scrolling. Over n minus 1 times n plus 1. this is the answer. I am not going to multiply out the denominator. It's actually preferred when you're dealing with rational expressions that you leave everything in factored form. So I'm not going to write this as n squared minus 1, although you can if you want to take that extra step, but there's no point. In example B, we're doing division, so remember when you divide fractions, you have to change it to a multiplication problem. So it's always keep the first fraction, change to multiplication, flip the second fraction. So keep, change, flip. I am going to write this as a multiplication first before factoring. Now you can do both at the same time if you wish. I tend to, when I start factoring, forget that I have to do the flip. So I want to flip first, change to multiplication and flip, or another way to say this is multiply by the reciprocal. And now I'm going to go ahead and factor since it's now a multiplication problem, and I can simply factor, cancel, and then multiply. Numerator is going to be x minus 3x plus 2. When factored, denominator difference of squares, x plus 1, x minus 1. Times second expression factors as x plus 1, x plus 1. And then difference of squares would be x plus 2, x minus 2 in the denominator. Now I can see that x plus 1 cancels. And I also have an x plus 2 top and bottom. And I believe that is it. So numerator is going to be x minus 3, x plus 1. Denominator is going to be x minus 1, x minus 2. Again, this is it. I am not going to multiply it out. It's actually a waste of time to multiply it out. Now let's review addition, subtraction. Remember, these are fractions, so when we add, subtract, we have to have the same denominator. The easy thing would be to simply multiply the two denominators together to get a common denominator. But these are rational expressions. If I multiply, look at the first one. If I multiply the 2y plus 4 times the y squared minus 2y minus 8, it's a binomial times a trinomial. It's going to be a big, huge mess, and I don't want to do that. So instead, what I'm going to do is I'm going to factor, and I'm going to find the least common denominator that I could use, just to simplify my computations. Again, you don't have to do it that way. You could simply multiply the two, but remember, in the end, we're going to have to factor and reduce these fractions. So we want to make it use the smallest denominator possible. The 2y plus 4 I can factor out of 2 to get y plus 2. Y squared minus 2y minus 8 factors as y plus 2, y minus 4. Oops, I wrote 6. Y minus 4, sorry. All right, so it looks like if I wanted to build these fractions up so they have the same denominator, they both have a y plus 2. But the first one is missing the y minus 4, and the second one is missing the 2. So when we talk about the least common denominator, in this case it's going to be 2 times y plus 2 times y minus 4. That's the smallest denominator that I can use. So I'm going to simply take the first expression and multiply by what's missing, which would be the y minus 4. And I'll multiply top and bottom by y minus 4. Oops, that's a parenthesis. And I put parentheses to remind myself that I'm distributing. Notice that I'm using the factored form of the denominator, and that's because in the end I want to double check to make sure if I can reduce, so I want to keep everything factored. Don't multiply that denominator out. And in the second one, it's missing a 2. So if I simply multiply this second expression by 2 over 2, I get 2 over 2 times y plus 2, y minus 4. All right, so same denominators. In the numerator, we're going to get y minus 4 times y minus 4 plus 2 over my LCD, which is 2 times y plus 2 times y minus 4. You may want to cancel the y minus 4 top and bottom, but you can't. The reason why you can't is because the numerator is not completely factored. You can only cancel if everything is factored. We have this plus 2 at the end, which is messing us up. So right now what we need to do is we need to multiply out the numerator. So y minus 4 times y minus 4 will be y squared. The minus 4y becomes minus 8y. And then minus 4 times minus 4 is plus 16. And we have a plus 2 over this LCD. And I can combine the 16 and the 2 to get y squared minus 8y plus 18 over 2 times y plus 2, y minus 4. Okay, can I factor the numerator? And I can't. That is prime. So nothing does cancel. This is reduced. So we've done the addition. We've checked to make sure that we can reduce it. And the final answer is y squared minus 8y plus 18 over our LCD 2 times y plus 2 times y minus 4. Let's move on to subtraction. Again, same thing. What's our LCD? If I factor the x squared minus 3x plus 2, it will be x minus 2x minus 1. The x squared minus 1, difference of squares, x plus 1, x minus 1. So our LCD is going to be x minus 2, x minus 1, x plus 1. That's the smallest denominator I can build both fractions up to. First is missing the x plus 1. We're going to multiply top and bottom by x plus 1. Again, I'm using my factored form of the denominator. Minus, the second expression is missing the x minus 2. So we're going to multiply the second expression by x minus 2 top and bottom. Again, remembering that it's distribution in that numerator. I'm keeping denominator factored. So same denominator. In the numerator, I have x times x plus 1 minus 2 times x minus 2 all over my LCD. And I'm just going to write LCD for now, because I still have to distribute the x, distribute the negative 2, and see if I can factor and cancel. So this becomes x squared plus x minus 2x plus 4 over this LCD. I don't know if you guys can hear this, but there's a cat fight outside my window. So x squared minus x plus 4. Okay, I'm going to pause for a second. X squared minus x plus 4, does that factor? No, it doesn't. So I know that this is not going to factor. I know that nothing's going to reduce, so I'm going to write my LCD back in there, which was x minus 2x minus 1, x plus 1. Notice the order really doesn't matter once everything's factored. That LCD could have been written in any order. And this is it. Did the subtraction, check to see if it was reduced. The last concept we're going to talk about in this section is complex fractions. Complex fractions are simply fractions within a fraction. In example 5, we want to simplify this complex fraction. It's not simplified because when you have fractions in numerator and denominator, it's not considered simplified. Now, if we look at this first complex fraction in part A, the fraction bar that separates the top from the bottom is division. So remember, fraction bars always mean divide. So this says divide the top by the bottom. So one thing you could do is you could rewrite this as 1 over x plus 1 minus 1 over x divided by 1 over x. So you have some choices. You can change it to multiplication and flip the 1 over x to x over 1. Or you can work within the parentheses and combine those two fractions first. I tend to avoid working with fractions as much as possible, so I'm going to avoid that by doing multiplication and flip and seeing what it looks like. Oh, so here I could distribute that x and get rid of the parentheses. And if I do multiply the first term by x, that becomes x over x plus 1 minus, when I multiply the 1 over x times x over 1, that's simply 1. But I'm going to write it as 1 over 1. Because the first expression is a fraction, and I know that I have to combine these. At this time, I would need to find the common denominator, and in this case it would be x plus 1. So the first fraction is okay. The second one I need to multiply top and bottom by x plus 1, which gives me x over x plus 1 minus, now remember this is in parentheses and you have to distribute that negative, so I'll do it in just a second. All right, same denominator. In the numerator, it's going to be x minus 1. So I'm just going to write that as negative 1 over x plus 1. And we can bring the negative out. Usually MyLab will want the negative in front of the fraction bar. But I don't think you would be marked off if you left the negative in the numerator, because those are equivalent. All right, so again, remember I said I was lazy and I don't like working with fractions? Well, there's another method that we can use. And this method is called clearing fractions. Now when we clear fractions, what we're doing is we're just multiplying. Remember, it is a fraction. We're allowed to multiply numerator and denominator by the same value. We're just multiplying by the LCD in the top and bottom of all the fractions. So you could use the LCD method, and this is the method that I typically use. I'm going to rewrite our complex fraction. This was 1 over x plus 1 minus 1 over x. All of this was over 1 over x. So if I were to look at all of these fractions and look at their denominators, I have an x plus 1, an x, and an x. So think about the LCD for all of these fractions, and it would be x times x plus 1. Okay, so I had fighting cats, now I have a bunch of chickens. Don't know if you guys can hear that. Anyway, it's a little bit distracting. So that's what I'm going to do. I'm going to take this expression, this 1 over x plus 1 minus 1 over x, and I'm going to multiply the top by the LCD, which is x times x plus 1, over the 1 over x. I'm going to multiply this by x times x plus 1. Because remember, This is a fraction. We can multiply numerator and denominator by the same quantity. So keep in mind that when I do multiply through, this is like multiplying x times x plus 1 over 1, x times x plus 1 over 1. I typically don't write it, but I know that it's over 1. So when I do the multiplication, I'm going to be multiplying the x times x plus 1 to the numerator. So notice that, ignore the minus 1 over x. Notice that if I were to multiply these, I would get x over x plus 1 over x plus 1. And the x plus 1s would cancel. I would just end up with x over 1, or x. And then distribute it to the 1 over x. And remember, this is a minus. When I multiply, the x's cancel and I get x plus 1 over 1, which is simply x plus 1. Over, in the denominator, the x's cancel, you have x plus 1 over 1, which is simply x plus 1. So what I've done by multiplying by LCD top and bottom in the beginning is I've cleared the fractions, so I no longer have to work with fractions all the way through. Now, it was a really messy first step, so if you're uncomfortable doing that, then go back to what we did the first time. This is x minus 1, or negative 1 over x plus 1. And I can bring the negative into the front of the fraction bar, but I'll just stop. So you can see once we cleared the fractions, it was very simple. So that's my preferred method. And I'm going to try this again with another sample or example. So in example B, we have 1 minus 1 over x squared minus 4 over 1 over x plus 2, again, complex fraction. We want to simplify this. I'm going to multiply by the LCD, but in order to multiply by the LCD, I want to make sure that everything is factored. And I'm going to rewrite this 1 as 1 over 1 minus. This is 1 over the x squared minus 4, difference of squares. It's going to be a plus 2 minus 2. Okay. All of this is over 1 over x plus 2. So I could see that my LCD is going to be equal to, look at all the denominators. I can build them all up to x plus 2, x minus 2. And that's what I'm going to multiply the top and bottom by here. I'm going to multiply the top and the bottom by the LCD, which is x plus 2, x minus 2. X plus 2, x minus 2. Again, if you want to remind yourself that when you distribute the x plus 2, x minus 2, that it's just going to multiply in the numerator, you can write over 1 over 1. Now when I multiply the 1 over 1 times my LCD, I can see that nothing is going to cancel. I'll end up with x plus 2 times x minus 2 over 1, or, in other words, x plus 2 times x minus 2. And when I multiply by this second term, so remember this was a subtraction. Oops, I wanted it in blue. This was a subtraction. When I multiply by the second term, it's x plus 2 times x minus 2 over x plus 2 times x minus 2. Everything cancels, and I just get 1. Multiplying in the denominator, I can see that this x plus 2 cancels, and I just have x minus 2 over 1, which is x minus 2. Okay, so I've cleared the fractions. Now I have to see if I can reduce this fraction. So remember, we can't cancel the x minus 2 because the numerator is not factored. We still have that minus 1. So we need to multiply it all out. It becomes x squared minus 4, right? X plus 2 times x minus 2 is x squared minus 4. And then minus 1 over x minus 2. That would be x squared minus 5 over x minus 2. I can't cancel using difference of squares in the numerator because that 5 is not a perfect square. I can't write it as something squared using integers. So this is done. It cannot be reduced. And that's it for this section R4.